Hello everyone, my name is Cole Lapierre of Separation Science. I'd like to welcome you all to our latest webinar in collaboration with ACD Labs. Our topic today is Expert Answers GC Troubleshooting and Method Development. However, before we begin, let me cover some administrative details. If you look toward the bottom right of your screen, you'll see a box to enter a question. You can ask questions at any point during the presentation by typing them into the box and clicking send. Questions will be forwarded to the presenter to be answered offline afterwards. Please note, submitted questions are not seen by the other attendees, so don't be shy about asking them. If at any time during the webinar you require technical assistance, please submit a question to request support. With that out of the way, let me introduce our presenter for today's webinar. Diane Turner is a Warwick University graduate who completed her Master of Science in Analytical Chemistry and started her career in environmental, then agrochemical science, later gaining experience as an applications chemist. Diane has developed methods and training within most industries globally for over 25 years. As a visiting fellow at the Open University, she continues disease diagnosis research from her PhD, along with food, drug, and space applications. Diane is a past president of the Royal Society of Chemistry, Analytical Sciences Community, and past chair of the Analytical Chemistry Trust Fund. Diane is a trustee of the Recycling Organization for Research Opportunities, amongst other committee memberships. Diane is a co-author of Gas Chromatography, Mass Spectrometry, How Do I Get the Best Results, and on the editorial board of the book series, Practical and Technical Guides for Lab-Based Chemists. Without any further ado, I will turn the presentation over to Diane.
Hello and welcome to this GC troubleshooting webinar where I'm going to be answering some of the amazing questions that have been coming through, problems that you're having with gas chromatography methods and instrumentation. So we're just going to be focusing on some of those today, and hopefully I'll be able to answer those questions. Actually, they might even lead to answering some of the other questions that you have as well. So thank you very much, first of all, to Separation Science for inviting me to give this webinar. So let's get started. So question number one was, what is the most effective expert-proven framework for systematically diagnosing common GC issues in real time? Now, I've been working with gas chromatography for more than 27 years now, and about half of my time is spent troubleshooting instrumentation, troubleshooting methods. So I'm going to take you through kind of the steps that I'm always going through when I'm thinking about, right, what's my problems? So of course, then you kind of have your step-by-step kind of guide you're going through. So first of all, you always want to identify what the problem is. So is it a real problem? I've seen plenty of people chasing their tails round and round, thinking there's a problem, and that isn't really, it's, you know, kind of something else. We want to gather information about that problem. So we're going to be talking about a little bit more about that in a minute, but we want to gather as much information as possible. Again, it's very, very easy to see one little problem, jump on that, and actually that's not the real problem, you know, that's just part of it. So we want to gather all that information to start with. We want to verify that our method and the instrument settings are correct. You've been there, I've been there, when some methods got changed and actually you haven't run your method to analyze that sample in quite the way that you should have done. So always double check that the correct method's been used, the correct settings have been used. So, you know, real question is, do you trust your colleagues? Have they gone and edited your method? Then you want to identify and check your symptoms. So yes, there's a real problem. Yes, it's not because it's been analysed in the wrong way. So there is a problem with the instrumentation. So let's just verify, first of all, what our symptoms are, what the problems are, and the symptoms of that. And again, remember, don't get very blinkered into one place. Look at all those different symptoms to start with. So we want to have a really big, thorough picture. We then want to go and isolate and test different sections of the instrumentation. So I'm going to go through in a little bit, in a minute, just how to break down that instrument into different parts. If you look at instrument as a whole, there's lots of different things going on. So what we want to do is try and think about, could it be caused by something in this area or this area or this area? So we want to narrow those down. If we do find a potential fault, we are going to go and repair that problem. We want to go and replace that consumable item, and we want to try and fix that problem. But we need to make sure that we properly test that the problem has completely been solved. So it might be that this bit that you found, yes, it's done a partial fix or a temporary fix, but it's not really solved the whole problem. Now, so therefore then we would have to go back to the next spot and find the next potential fault and fix that and test it. So once we're happy that we've properly verified that the instrument's now working, then we want to properly go and record any actions taken. So 90% of problems are caused by what was last done to the instrument. So either that's a sample analysed or maintenance performed. And of course, that also includes troubleshooting. And decide if any preventive actions need to be implemented to prevent this problem happening in the future. Maybe it's just something a consumable had not been replaced when it should have been. Or maybe you don't normally replace this, but you think actually now we should be doing this on a more regular basis. So what preventive maintenance actions can you then put into your how you run your instrument, how you look after the instrument to prevent that from occurring in the future? So that's kind of a little bit of an overview of going through our whole troubleshooting procedure. So let's have a little bit look more info, a little bit more detailed look. So one of the things in gas chromatography, bits of information about a problem, is looking at your chromatogram. Now, I always say being able to read a chromatogram is as important to GC as being able to read a book, for example. So when I get sent a problem, and somebody says, can you help me? I've got this problem. First of all, I'm really thoroughly trying to find out what that problem is in the first place. So part of your preparing for troubleshooting, you will always have a problem, is to actually record what things should look like, and that includes your chromatogram. So the first thing I say is, please send me a chromatogram of what it should look like and a chromatogram of what it looks like now, and that can really help me to identify what the problem is. Now, when I'm comparing the two, the first thing I don't look at is the peaks. The first thing I look at is the baseline here at the bottom. Now, the baseline is a measure of the health of your gas chromatograph. So what you want to be doing is having a look and saying, is that baseline flat? Has it shifted upwards than it is normal? Has it gone and got more column bleeds? So baseline rises a lot higher than it normally is. Is it really noisy like this? So is it kind of wandering all over? And if it is quite noisy like that, does it have a certain pattern to it? Or is it just really, really random? So that's the first thing I want to have a look at. And again, we'll be using that information later on with some of the questions and troubleshooting those. So once we're happy with the baseline, yes, it's where it should be, we've got the right amount of noise level, etc., then we can now start to look at our peaks. And when we look at the peaks, of course, we've got a number of bits of information to look at. So first of all, the retention times. Have the peaks shifted earlier? Have they shifted to later? Is it all of the peaks, or is it just some of those peaks that have moved? So we're looking for patterns as well. If it's some of those peaks have moved, then starting to think about why could it be those compounds have moved, those peaks, but not others. So that's when you start to go into the chemistry of those compounds. Is it the ones that have moved are more polar and the ones that haven't moved are less polar? Or is it something to do with volatility? So maybe the earlier peaks have moved and the later peaks haven't, or vice versa. So try to pull that information out as well. So really look at the chemistry, so the chemical properties, the physical properties of those different compounds. Next thing to have a look at is the shape of that peak. Is it a really nice narrow peak, which is as it should be, which we can see with peaks number 1 and 2, or is it become broader? So again, then peak number 3 here, highlighted in yellow, is a much, much broader peak. Now, it could be that that is quite normal for your chromatogram, which is why you need that reference chromatogram to know what it looks like when it is working well. But is it that some of the peaks have broadened? Is it all of the peaks that have broadened? If it's just some of them, again, think about the chemical and physical properties of those molecules. So we've got all of that bits of information, and the other things to have a look at is your peak shapes. So are your peaks tailing? are they fronting? So again, then we should have really nice Gaussian peaks. So you can see at the top right-hand side of the screen here, we've got a tailing peak. So that's why the right-hand side is wider than the left-hand side. That means that you have more molecules traveling slower than average through your system. And that either means activity or a dead volume. We're going to be looking at with one of the questions in more detail later. And the bottom peak there, so the bottom right-hand corner there, is a fronting peak. So that looks a bit more like a shark's fin. And you can see there that the left-hand side is wider than the right-hand side. So that means that more molecules are traveling faster than average through our system. So that means that we've overloaded something. So that could be that we've overloaded the column. If you're doing something like thermal desorption, maybe you've overloaded your cold trap, for example. So we're to be looking at those peak shapes. It could be that their peak shape, it doesn't even look like a peak, it looks like a wobbly mess. So again, then you can say, well, actually, maybe it's not focusing properly on the column. So you've got to be thinking about then, looking at the peak shapes and thinking about what the problem is. So you want to look at the peak shapes in terms of how broad they are or how narrow, and if they're tailing or fronting, as well as their retention time. Another thing we want to be having a look at is the number of data points across the peak. So we ideally want between 10 and 25 data points across the peak to really see the outline of the peak. Now, if you have coeluting peaks and you don't have enough data points, then it could be it's not then being able to pull out and acquire the data fast enough to see the outlines of those two coeluting peaks. And if you're using something like GCMS and deconvolution, it's going to make it harder for deconvolution as well. But also, it's going to affect the accuracy of your integration. So if your peak looks a bit like a child's join the dot drawing, so very angular and not a nice Gaussian curvy peak, it could be your acquisition rate is not high enough. So that's going to affect things like your reproducibility. Now, if you've oversampled your data, you've got too many data points, then what will happen is your sensitivity will decrease because the noise increases. So again, then by having a look at your peak, if it starts to look kind of, again, slightly wobbly sides, etc., so kind of slightly noisy peaks, that your acquisition rate is too high, and you are going to lose sensitivity as well. So that's a good indication. So lots of information can be gained from your chromatogram. So you're thinking about then, your chromatography, your separation, of course, as well, your peak shapes, the retention times. And of course, when you do identify a peak that is a problem, we're going to be then relating that to the chemical properties. So functional groups, is it polar or non-polar, but also the physical properties as well, like volatility. So now we've got and identified and we've pulled some information together. I mean, there could be quite a lot of different problems in that. But the main way you're going to solve that problem is to really know your instrumentation to start with. So whenever I'm giving training and I send people back to their own laboratories to look at their instrumentation, you want to be looking at two different flow paths. So the first flow path is our carrier gas flow path. So what's the source of your gas? Is it a cylinder or a generator? How does it get to your instrument? Does it go through any traps and filters? Where does it go in the back of your instrument? How does it get to your inlet? And of course, that's where your column is going to be installed. The carrier gas will then flow through the column and through into your detector. And of course, through that flow path, you want to identify each of the different parts. What type of carrier gas are you using? What type of inlet and what types of traps and filters? What type of column? And also what type of detector? It might be also that you've got splitters en route. It might be that you have an optimized T for doing things like backflushing. So again, identifying all the different parts of your instrumentation is really important. Now, this has a very simple liquid autosampler sitting on it, but it could be you have a different type of autosampler, like for example a purge and trap or a thermal desorptor, or even a headspace instrumentation. So for some of those types of instruments, the carrier gas might also go into the GC and then back and out around that autosampler and back then into the column, directly into the column, or back into the instrument and through the GC inlet. So again, then you've got to think about your carrier gas flow path at that point as well. Now, of course, the main problems with our carrier gas are leaks. So again, then identifying where all the different connections are, and again, getting to know that instrument when it's working well will help you to then go and troubleshoot it once you have got a problem on there. So that's the first flow path we want to really understand, is our carrier gas flow path. The second flow path then is our sample flow path. So for example, we're going to take a simple liquid autosampler. So first we have got to get our sample into the syringe. Then we've got to go and get it out of the syringe into the inlet, where we're going to vaporize that sample. Then we have to transfer those molecules from the inlet onto the column in a narrow sample band. And that means that all those molecules of the same compound are close together and can give us sharp peaks. Then we've got our separation through our column and our GC oven. Then it goes into our detector, where it's detected our peaks. And of course, then our signal goes across to our PC and our software, where we can look at our chromatogram. And of course, if we've got GCMS, then we'll be looking at three-dimensional data. So again, then we can start to think about then the problems can occur in those steps. So for example, getting all of that sample into a liquid autosample into the syringe without an air bubble is our first step. Then we've got to make sure that we get everything out of the syringe into the GC inlet. And if it's a hot GC inlet, we might suffer from mass discrimination in our syringe. Then we've got to vaporize that sample. So we want to vaporize the sample without any thermal degradation. And we want to transfer our analytes onto the column without any mass discrimination, meaning that then we want to transfer all of the analytes, no matter what their molecular weight, including the higher molecular weight compounds, onto our column. But we also want to be trying to keep all of the dirt and involatile material inside the GC inlet liner, which is much easier to go and replace than going and trimming our column, as we'll talk about later. Then once we've got all of those analyte molecules on our column in that nice narrow sample band, meaning they're all close together to get sharp peaks, then we've got to optimize our separation through that column. So optimizing our oven temperature program. And of course, then we've also chosen our GC column dimensions and type of stationary phase. Then we're going to elute them into the detector. So again, then they need to go straight into that detector, and the position of the end of the column needs to be optimal for the type of detector that you have. If the column's not in far enough, what you usually get then is mass discrimination. So you'll lose your higher molecular weight compounds, you'll get band broadening of them because you're going to have a dead volume in there. If the column is in too far, it could interfere with the operation of that detector and cause all sorts of problems, from actually having no detection and no peaks through to having some noise in our baseline. So again, then we've got to think about the position of that column into the detector. And of course, we shouldn't forget our software. How we got the right acquisition rate? Are we collecting the right data and the right information? Have we got any thresholds being set? What about our integration parameters? Is that the problem? So we can then break the whole sample flow path down into multiple different stages, from our autosampler, our inlet, our column, our detector, and our data analysis system. And again, of course, you might have some extra steps in there depending on the type of instrumentation that you have. But in terms of that sample flow path, we can look at it from a thermal point of view. If each step is too hot, we can get thermal degradation. If any steps are too cold, we can get a cold spot, and that will cause problems for our higher molecular weight compounds. We can also look at that sample flow path from an activity point of view. So if we have any active sites within that flow path, then those more polar compounds are going to be more likely to get stuck, especially any sulfur species. So again, then so you can look at that sample flow path from two different points of view, and again, relate that again to our physical and our chemical properties of our molecules. So knowing the instrumentation, knowing how each part of it works, what parts they play in the analysis of your sample is really, really important. And if there are any parts that you don't understand, then that's where you really want to go and get some training, because it's really going to help with your troubleshooting. So that leads me on to question number 2. And this is, how do you distinguish between problems caused by the injection system, the GC column, and the detector? So first, with this question, we've already broken it down to the injection system, but what do we mean by injection system? Does it mean the autosampler? Does it mean the GC sample, GC inlet, for sample introduction actually onto the column? So again, then we can break that down into two parts, the GC column itself. Is it the column or is it the carrier gas flow rate? The type of carrier gas, or is it the oven temperature program that's going to be causing the problem? So that GC column again could be multiple different parts. And of course our detector. So there's more than 20 different detectors. And of course we also can hyphenate GC to mass spec. And again, that's going to be causing lots of potential for lots of other problems, which we're not going to go into today. We're just going to focus on gas chromatography. So let's have a think then about how we can distinguish between this. And again, this is going to then really be understanding the different instrumentation parts. So of course, then we have our carrier gas flow path, as we talked about with that previous question just on there. So one of the key things then is looking at our chromatogram and what is the problem. If it could be things like we have contamination, for example. So contamination generally will be, if it is individual peaks of contamination, it's either going to be our sample, our autosampler, or our inlet. How do we know? Because they most focus on the head of the column to be peaks. Whereas if it's constant in the background, it could be our carrier gas, it could be our column, it could be our detector. So we've got kind of different things again. So just think about how it's all working. Yeah, so if it's in terms of peak shapes, then our peaks have to then condense on the front of the column in that narrow sample band. So generally, if that's probably, then it could be the introduction to the column. Or of course, then if we're starting to get things like peak broadening, it could be the sample introduction, or it could be the column or the oven temperature program is causing band broadening. Now, if it was working perfectly well before, it's probably not going to be the oven temperature program. It's probably going to be more likely to be our GC column. And of course, then if it's things like mass discrimination, that is usually going to happen with things like going from different sections, from the autosampler to the inlet, from the inlet onto the column, from the column onto into the detector. That's usually going to either be a physical problem, like a band broadening, and so therefore then it's going to be a kind of like diffusion into that space. So it's usually going to be a dead volume, or it's going to be things like, kind of a chemical problem. So that's usually going to be a little bit more tailing on there. So you can think about it in different ways. So that question is quite open-ended. It could be quite a few different possibilities just on there. But one of the key things then is dividing it up and going, right, what problem am I seeing? Could it be being caused by the autosampler, the inlet, the column, or the detector? And of course, that very much depends on the problem just on there. So let's have a look at an example of poor sensitivity. So we've got our normal chromatogram at the top just there. So we can see our baseline, we can see our peak separation, we can see our peak shapes, and we can also see the relative ratios just on there. And then we've got our problem at the bottom. So the first thing we want to go and do is look at our baseline. So the baseline looks pretty much the same just on there. Look at the solvent peak, looks about the same. And our first peaks look fine, and all the peaks are there. But what is the problem is the peaks towards the back end of the chromatogram are smaller. So it's the last three peaks really are the problem. Maybe a little bit of the one before, the fourth to last peak as well. So we've got smaller, later eluting peaks. Now, if these were all hydrocarbons, okay, it could be a physical problem. So that means it's more mass discrimination. But if it is something like, kind of those are a different class of compounds, and maybe those are more polar compounds, whereas the others are non-polars, then it could be a chemistry problem of maybe those later eluting peaks are getting absorbed. So if it's discrimination, then it could be a series of different things. So we could get discrimination, so mass discrimination due to the splitless time. So if you're doing a splitless injection and you close that open the split exit before all your compounds have transferred across, quite often you'll see problems across the board, but sometimes if there really is kind of a big difference in molecular weight, then it could be those later eluting peaks are actually then going to take longer to vaporize and transfer onto the column. So that could be a problem. It could also be actually those high molecular weights are suffering from from syringe mass discrimination. So what happens then is when we put our syringe into a hot inlet, when we have a very volatile solvent, and we push down the plunger, the solvent doesn't squirt out the end of the syringe as we imagine, but it evaporates from inside the syringe needle because the needle's been inserted into a very hot inlet, and of course it heats up, and our molecules, our solvent molecules, will then evaporate from inside the syringe needle. Our volatile compounds also will evaporate quite easily, but what do you usually do? You push down the plunger and you remove the syringe straight away. And of course, those higher molecular weight compounds are going to take longer to evaporate, so it's going to have to get the needle quite hot to be able to evaporate them and to come out into our GC inlet. So what we're effectively doing is removing the syringe containing those high molecular weight compounds. So that's called syringe mass discrimination. Could also be that you've got the incorrect setting on your inlet. So the inlet temperature is a little bit low, and that means that those higher molecular weight compounds are essentially, they're not, some of the molecules are transferring across, but not all of them, and we're not getting 100% transfer. So some of them are being left behind in our GC inlet. So we can get discrimination just on there. So usually then transferring, once it's onto the column, it's on the column, and it's not a problem. But we can also have problems on our detector. So if our column's not in far enough and we've got basically a dead volume, what happens is, say for example, it's a flame ionization detector, then what's going to happen is our molecules come out of the end of the column, they then diffuse. And of course, the higher molecular weight compounds are trying to go against gravity, they're more affected, they will go like this and stick on the inside of your jet and not actually make it up into the flame, whereas your more volatile compounds will travel much further and get into that flame, and of course we won't have so much diffusion of those. So it could be then column detector at column position in your GC detector. Sometimes though, depending on the types of compounds, it could be the column position in your inlet. And of course, it can also be things like absorption effects in your GC inlet as well. So you might have gone and had some irreversible absorption on your GC inlet. Now we see that the peak shapes are still the same, which means that then it's not going to be so much activity on our column. It's more on our inlet, and we're probably suffering from irreversible absorption there. But we also want to be looking at our peak shapes. So it could be those peaks look shorter, but the area has not actually changed, so they just become broader. So if our peaks have broadened, and our area is the same, it could be that the pressure flow has changed, but usually that will affect the retention times, along with the temperature ramp on the oven, and of course the injection technique as well. So again, some of those problems you'd be seeing other symptoms as well, like retention time shifts. So as I was talking about earlier, we want to gather all the symptoms before we then jump to that a conclusion about what it possibly could be. But hopefully this kind of gives you an idea of how we're working through it. Yeah, so we're working step by step through the different modules, thinking about, could this cause the problems of what we are seeing? And again, then identifying then the chemistry and the physical properties of the molecules which are affected. So that takes me on to question number 3. So question number 3 asks, if peak tailing suddenly appears in a method that previously performed well, what systematic troubleshooting approach would you then go and recommend? So we've had a good peak shape, I assume. So we get nice Gaussian peaks, it all looks really good. And then we start to get peak tailing. So again, then what I would be first of all asking is, what compounds are tailing? Is it everything? Is it just certain classes of compounds? So peak tailing can be caused by 2 problems, by activity, but also by dead volumes. So we want to know about the properties of those molecules. If it's affecting everything, then that's great, but activity would not affect our non-polar compounds like hydrocarbons, because they will not have any absorption effects. They won't have interactions like hydrogen bonding in different places, whereas our polar species will. So we need to, again, just examine and have a look at in more detail about the types of compounds that they actually are. So as I mentioned then, our peak tailing, as we looked at earlier, is when the right-hand side of the peak is wider than the left-hand side of the peak when taking the apex into account. So if it is a chemical problem, i.e. more polar species, that means we're going to have activity in the system. So it could be that we've got absorption on an active site. So most of our active sites are going to be in our GC inlet or on our GC column. However, it also depends on the type of autosampler that you have. So again, then if you have things like different packing materials in thermal desorption tubes, again, that can have some activity on there and cause those tailing peaks as it transfers across to the GC column. So again, we've got to take our type of autosampler into account as well. It does mean that molecules are taking longer to elute, and the biggest problem, of course, with our tailing peaks is that we're going to get band broadening. So when our peak gets broader, what's going to happen is it's going to co-elute with neighbouring peaks, but also it gets shorter, which also means that our detection limits are going to be lower, higher as well. So we won't get such good sensitivity. So that's our activity in our system, and that only affects our more polar species. However, dead volumes can affect both polar species and non-polar species. So dead volumes are unswept areas, which then those molecules gradually bleed out. They join the end of the peak, as we see just here, and we're going to be having a look at that in more detail on the next slide. Now, one very good example of a dead volume is in your GC inlet. So when we are doing, for example, a splitless injection, once we've transferred all the compounds of interest, we almost always must go and open up our split exit, because what we'll have is a dead volume around the outside of our GC inlet liner. And when we're doing a splitless injection, of course, we have very low concentration sample. That means that the majority of our sample is going to be solvent. So what we do then is we open up the split exit, it flushes the outside of the liner out of the split exit, and we then get good peak shapes. Now, the chromatogram bottom left is actually a real chromatogram I had from a customer a number of years ago, and they've given me permission to use it. Now, what we can go and see is we can see our solvent peak, and on the right-hand side of that solvent peak, there's a little bit of a shoulder just on there. And that's actually the moment when the split exit went and opened. However, the split exit over time can get blocked because, of course, you're flushing everything out of there. Now, your very volatile compounds will go to your split line trap, but your less volatile compounds will basically condense in your split line. So what happens then is it gradually gets blocked. I always call it coronary tube disease. So basically it gets smaller and smaller. And over time, when the instrument gets older, it can gradually lead to a blockage. And that shoulder that you can see is where the split exit opened, but because it was blocked, it did not flush the outside of the liner. So those solvent molecules gradually got back and went onto the column, and you can see then that you've got a very long solvent tailing peak. Now, it's a tailing solvent peak. Now, those peaks that you can see on there will also be tailing a little bit, but remember, they're much lower in concentration. So what you really see is a solvent peak tailing. And of course, that's interfering with the separation of those early eluting peaks. And that's all just basically due to a blocked split line. So that's again, a very good example of a dead volume in our system. So whether you haven't gone and opened a split exit in your splitless injections or it's got blocked, then you can get the same effect just on here. So let's think about a dead volume, but also as well about what's happening with that activity as well. So what we've gone and we've got this lovely Gaussian peak, and it proceeds along, for example, the column, or it could be through the GC inlet liner, or through your autosampler of different types. So it goes along, but it meets then an unswept volume or an activated area, as we can see in the middle picture just in here. So it could be then that unswept area, some of the solute mass diffuses in there, or it could be that this is an active site. So some of those molecules can get absorbed or interact, for example, with hydrogen bonding just on that. And that means then, as the rest of the molecules that haven't been diffused into that dead volume or haven't interacted, then they move past that unswept area or that active area. And those trapped solute then will gradually diffuse out and join the back of the rest of those molecules and give you a set tailing peak. And the same with an active site as well. So eventually then those molecules will come off that active site, unless of course you've got irreversible absorption, and then you'll just get a smaller peak. But again, if they come off, they have a stronger interaction, that means that they're going to travel slower through the system, and they will then join the back of that peak, and we'll end up with that tailing peak. So with dead volumes, they affect everything. But active areas will only affect those compounds that can have that interaction, whether it's absorption or hydrogen bonding. So usually it's more polar species that you're going to have then, which are going to suffer from activity. So what could cause tailing peaks? So we're really here then we're looking at the sample flow path. So the sample flow path, of course, again, could be around your autosampler, could be in your GC inlet. So particularly polar species, the liner is made of glass, and so therefore you can get hydrogen bonding, but dirt anywhere in the system can also cause tailing peaks. And of course, the most likely place to get dirty is going to be that GC inlet liner. Now inside your column, if you've got a few silica column, again, you're going to have activity, but deactivation should help to reduce that. But as your column gets older, of course, the column will get damaged, you'll get used, and then that deactivation can be lost, and as well as the stationary phase. And so therefore, then you have those active sites through your GC column just on there. So you've got activity in your column. Now, even in some detectors, you can have activity. So with a mass spectrometer, you can have some activity in the ion source, for example. That's where you usually then lose molecules rather than get those tailing peaks. But tailing peaks are caused by, is generally going to be before your detector, because then those molecules are traveling slower through your system. So generally your autosampler, your inlet and your column. But the first place to always start is usually your GC inlet liner. The liner itself is usually the place going to get dirty and become active first. So that leads me on to question 4. How do you know when it's time to trim a column? And what is the most efficient way to age or condition a chromatographic column? So we've covered a little bit of this question in the previous questions. So of course, if you've got activity on that column, the most likely place on your column to get damaged is the front end of your column. So if you've gone and damaged it, then of course you're going to lose some stationary phase, you're going to get some activity. And again, this is going to be most apparent with those active compounds, the more polar species. So again, then we're thinking about our carrier gas flow path, we're thinking about our sample flow path. Now, when we're developing our method, we always want to try and keep that dirt inside the GC inlet liner, which will replace more frequently. But depending on the temperature of your inlet, of course, the end of the column is inside that inlet. And so, of course, it's going to get damaged by the inlet temperature, which should make sure that the inlet is never above the maximum isothermal temperature of that column. They're also going to be transferring our analyte molecules onto the front end of the column, and we're going to be condensing them there. In particular, we're going to be condensing the solvent. Now, if you've got quite a high inlet temperature, and you might also be getting some dirt on the front end of the column, and that can also damage it as well. And of course, then that's going to affect your chromatography. So we're going to get things like our tailing peaks. So tailing peaks is a very good indication that you need to do some maintenance. But as mentioned in the last question, the most likely place to get some activity which causes our tailing peaks is in the GC inlet, because that's where we're trying to trap our dirt. So we need to go and do that inlet maintenance first. Now, when you take your liner out, you can see the dirt has gone beyond into the very bottom of the liner. That will also mean that some dirt will be on your column, and that's the time to go and trim your column. Now, maybe you didn't see some dirt on the front end of the column, but you've done your inlet maintenance and you've still got some tailing peaks, and again, that's another good time to go and trim the front end of that column. So if you've got tailing peaks, again, inlet maintenance first, trim a little bit off the front end of that column. Now, it hopefully will have improved, but it might still be having a problem just on there. So what else can we go and do to our column to perform some more maintenance? So we could trim a bit more off the front end of the column. Now, how much you can trim very much depends on the length of the column. So for example, if you have a 60-meter column, trimming a meter off the front wouldn't be so much of a problem. But if your column's only 10 meters long, that is going to be a problem. You can also try reconditioning with reverse gas flow, so back flushing it overnight at the maximum isothermal temperature. That's what I did very much in the early part of my career when I wasn't properly optimizing my inlet temperatures. So that was quite routine to go and do that when there's a damaged column, and you can still go and try that if the trimming hasn't happened. But of course, you've got to make sure that it's definitely the column before you do any of this. Now, if you have a really bad damaged column and you think, right, I'm going to have to replace it, you can try one more thing to see if that will help. And that's by rinsing the column with a solvent. Some of the manufacturers do so that you can do this. So it's usually a 9:1 methylene chloride to methanol, so, or dichloromethane to methanol, depending on which country you're in. But it can only be undertaken with cross-linked or bonded columns. So always read the columns and the manufacturer's instructions. When you go and flush it, then the solvent flows in the reverse direction to the carrier gas flow, and the solvent then is pushed through the column under positive pressure, and it basically flushes the column out. You then need to go and dry it before you heat it, because of course there will be residual solvent in there. And the best way to dry it is just to pass carrier gas through it at a low temperature. So this is an example of our chromatogram before rinsing on the left-hand side, so number A. So this is after quite a lot of on-column injections of pesticide extracts. And of course, on-column injection, you're going to be transferring all of that dirt onto the column as well. So that means that then you're going to cause more damage. Then after back rinsing of the column with a 9:1 mixture of DCM to methanol, we can see chromatogram number B. So that's after rinsing, so we can see that the baseline has very much improved, our peak size, our peak shape, our separation, all of those have very much improved. I always say though, if your column is pretty much dead and you're going to have to replace it anyway, it's always worth trying solvent washing your column to see if that improves it and see if you can then extend the lifetime of your column. So with our column conditioning then, so this is when you have a brand new column or your column, you'd removed it and you're reinstalling it then. So when we are conditioning a column, usually it's to remove our excess bleed, and it's always going to be a longer period of time if you have a more phase, so thicker stationary phases, or a longer column, or a more polar column. Pre-use according to the manufacturer's instructions, but if you can't find the instructions for conditioning, then you should never go above the maximum isothermal temperature overnight. That's the maximum amount of time that you'd be doing that. If possible, try and condition it not connected to sensor detectors like mass spectrometers, because it will dirty the ion source. So if you have an FID, try and install conditioning in that first. So when you first install your column, install it into the inlet, and if possible, turn the gas on. But if you're using hydrogen as a carrier gas, you must not turn the carrier gas on until you've connected it up to your detector. So once you have, if you can turn on the carrier gas, then just check that you've got flow going through the column by dipping the end of the column, the detector end, into methanol. Now, when we're installing our column, what we're going to have is air in there. Oxygen will damage stationary phases, it oxidizes it at higher temperatures. So you must always purge out the oxygen at ambient temperatures first. So I always purge it out at 30 degrees C. Now, it could be 10 minutes to purge it, it might be 30 minutes. So the longer the column, the longer you will need. The thicker the stationary phase, the longer you'll need. And the more polar the stationary phase, the longer you'll also need. So again then, around about 10 to 30 minutes. Purge then the moisture out next. So usually the moisture will not purge out at ambient temperature. So what you need to do is just gently heat the oven up at 10 degrees C per minute to about 100 degrees C and hold for the same amount of time. So now you've removed the moisture and the oxygen out of the column, which will damage the column if you heat it really high. So never install it and heat it up to the maximum temperature straight away. You need to purge that air out first. And then the final step is to condition the column to remove any excess column bleed, but also any contamination. So if you've left it around open in the lab for a while, you're going to have things like hydrocarbons in there and all sorts of compounds from the lab will have diffused in there. So you want to purge that out. So you usually want to heat it up to about the maximum isothermal temperature or just below the method final temperature, ramping up gently at 10 degrees C per minute. and hold it then until the bleed stabilizes. So what you'll see is it goes up and it goes down, and then it will start to stabilize, and that's when we can stop it. Which is why, again, connected to an FID, you can have that running, and then you can see where your bleed is at. Otherwise, I usually hold it for an hour. So moving on to question number 5. For a lab running multiple compound classes, for example, FAMEs, phytosterols, and waxes on the same column, what maintenance schedule maximizes the column length and lifetime and the data quality? And when do you recommend switching to dedicated columns? So when we've got a wide range of different compounds, the thing is we want to be thinking about is what is going to cause the most damage to our column. So columns can be damaged by water, hence we're purging the moisture at low temperatures, oxygen at higher temperatures, inorganic acids or bases or organic solvents. So we want to try and make sure that our instruments leak tight and we're not introducing nasty compounds into our GC column. If you are, then you'd expect that your column will not last as long. If the column maximum temperature is too high, so always use the maximum isothermal and the maximum ramping temperature for the different parts of the instrument. So for example, the inlet and the detector should not go above the maximum isothermal temperature because they're held at a constant temperature, whereas the oven can go up to the maximum ramping temperature for shorter periods of time. If you have any gas or matrix contamination, so again, that can be a problem, so make sure your carrier gas is nice and clean. Think about sample preparation to remove the matrix. And again, think about your inlet temperature so that matrix doesn't get on the column in the first place. Cracked or broken, so potential leaks in the system, so treat it well. Other problems could be things like you've got contamination there, so think about wearing gloves, clean the end of the column with methanol if you've got any dirt. Now, if you put a septum to position at the end of the column, that residue, as you go and trim the column, could now be inside the inlet, so always be careful of things like that. And of course, a power cut could happen at any time, so because oxygen then will get into your column. If it's at a high temperature, it will damage that column. So try to keep the oven temperature cool when you're not using the instrument. So usually a standby method is very good for that. So if you've got lots of high molecular weight compounds, if you've got lots of matrix, etc. in there, then you could think about using a guard column. So this is used to protect the column stationary phase from our non-volatiles, and it prevents cleaning or trimming of the analytical column. So what you're going to do then is just trim off the guard column, and of course you've still got the same amount of stationary phase in there, and you're going to get less stationary phase bleed. So you can get columns which are integrated. So for example, you could purchase a 30-meter column with an extra 5 meters of guard column on the at the front end. And our guard column itself is deactivated fused silica. So it's got no stationary phase, but those silanol groups are deactivated. So if you go and trim 60 centimeters off a guard column, then the retention time's only reduced by about 3 seconds because of course we're not affecting the amount of stationary phase in there. But without a guard column, you would be trimming off the stationary phase, so you get about 2.5 times greater retention losses. And with a guard column, it's very easy to estimate losses when removing consistent lengths. And you can actually calibrate columns of how long you've got them. And then when you trim the column, you can just say how much it's trimmed. And if you're using a constant flow method, it will then adjust the pressure for the length of column that you have. So a guard column is very good if you've got quite dirty and high molecular weight samples to protect your analytical column. Now, if you are transferring some of that dirt onto the column and you can't prevent that, and getting it onto the guard column can also cause some problems because it's very high molecular weight. It might just sit there and cause problems with shifting retention times. Then you can think about back flushing your column in between the runs. And that means that after all your compounds of interest have eluted from your GC column, you usually stop your GC run and you enter backflush mode, which basically then changes the direction of your the carrier gas flow through your column, and it flushes those unwanted compounds through the GC inlet split exit and goes through to waste. So they don't go through those higher molecular weight compounds aren't going to go and damage the rest of the column or dirty your detector as well. So if you imagine the lower the volatility of those analytes, the less distance they will have traveled through the column and into the column when you're separating and detecting your analytes. Therefore, it's much faster to back flush it via the inlet than it is to burn it off through the entire column. And reverse column flow can be very, very fast, and it's detector dependent. So if you've got something like a vacuum, like a mass spectrometer, then we can't then use as higher flow rates to back flush as we would for something like an FID. But of course, you do need an extra device in there, like a purge splitter, to then reverse the flow of gas through the column. So it does need some additional instrumentation parts, so modules, to be able to enable this. But that is your kind of extra result. But if you can control it through optimizing your inlet temperature and regularly changing that liner, then guard columns and back flushing might not be necessary. So maximizing basically your column lifetime, think about it then. So first of all is leaks. So making sure that your system is leak free is very important, and think about your dirt. So if you've got a lot of high molecular weight matrix, can you remove it in sample preparation? Can you remove it with the type of water sampler that you have? Can you then keep it in the liner by optimizing properly your GC inlet temperature so it doesn't get to the column? If it does get to the column, then how are you going to remove it from the column? Are you going to be doing trimming? Are you going to use a guard column and trim that? Are you going to do back flushing? And of course, then regular maintenance of things like your column and your detector, if they do get dirty, is important. Okay, so our next question is, when you see unexpected peaks in blanks, what is your systematic approach to determine whether contamination comes from the septum, liner, column, source, solvent, or sample carryover? So with a blank, I expect that you're implying that you have a solvent that you're injecting. So it's a solvent blank, for example, a liquid autosampler. But again, then it could be other blanks, like for example, with thermal desorption, a blank TD tube with no sample, could be a headspace vial with your headspace instrument, etc. So again, then here, what we want to be thinking about is, again, our different modules just on here. So when we went through the steps of troubleshooting earlier, we thought about those different modules in here. So what you want to think about then is, how can we isolate, for example, our autosampler? So we can isolate our autosampler by going and doing something like a blank run. So blank run is where you don't do any injections. We're just heating our inlet, and that all can be used to check your inlet and your column and your detector. Now, if it's that you've got extra peaks in your sample again, then you'd go to your solvent blank, so through your autosampler. But you can then start to think again, depending on the setup and the method that you have, you can start to isolate individual components just on there. So of course, then it depends on the types of peaks as well. So let's have a look at a few examples just on here of contamination. So again, our top chromatogram is what it should look like, and our bottom chromatogram is when we've got some extra peaks. So again, that could be from the solvent, it could be a solvent blank, it could be from your sample. We're seeing it here from our sample. So we've got additional peaks in there. And again, when we look at them, are they a good peak shape? What is their relative retention times? Are they early? Are they late? So therefore, their relative volatility. So we've got to think about the chemistry and the physical properties of that contamination to start with. And then we can start to think about our potential sources. So is it from our carrier gas? So if it's higher molecular weight, slightly less volatile molecules, they will condense on the front end of the column, and therefore we will see peaks in our chromatogram from our carrier gas. Whereas if it's gas contaminating, kind of gas molecules that are contaminating very volatiles, then you'd be in your baseline, which we'll look at in a minute. It could be the autosampler. So can we isolate the autosampler? i.e., we just do a blank run with no autosampler injection. If you don't know how to do that, so some software, you can just put a 0 in terms of your vial number, and it knows to do a system blank. Or you can just go and change in your method that you then are using doing a manual injection, and so therefore it won't use the autosampler, and it enables you to do that. Could be the inlet, liner, septum, ferrule. So if it's not the autosampler, we've isolated the autosampler and there's still those peaks in there, then the most likely place is going to be the inlet. So we'd go and do the maintenance of our inlet, to replacing the liner, replacing the septum, thinking about trimming the front end of that column and replacing that ferrule as well. Could be cleaning solvents in there. So again, what you're going to do is look at have we done any maintenance recently? Has it got extra contamination in there? Could it be the fingerprints? You've reinstalled the column, left some fingerprints on the front of the column. You haven't used gloves when you've replaced the liner, etc. You've got extra peaks in there. It could be things like plasticizers in your vials and a septum. And of course, if it was originally a solvent blank you're doing, it could actually be your solvent bottle is contaminated. So try a different one just on there. But the key thing with all of these is that the peaks are separated on the column. That means that they must be coming from before the head of the column, okay? Now let's have a look at our next example. So here we can see again our normal chromatograms at the top, and when we look at the bottom chromatogram there, we can see that we've got a higher baseline. Of course, that might be affecting our sensitivity, so our peak heights, it could mean more bleeding towards the end, but you can notice that the baseline is higher than normal. So our potential sources here then is it could be a leak. So if you've got a leak, then of course you've got oxygen going to the column, you're going to get more bleed, you're going to get a higher amount of column bleed in there. So we'll see that higher baseline. Could be carrier gas impurities. So these are too volatile to trap on the front end of the column. So they're going through all of the time. I recently had a customer where the wrong purity of carrier gas was bought. It's a 4.2 rather than a 5.5. And that really changed the baseline and also the sensitivity of the peaks as well. Could be our column bleed. So again, then if it's column bleed, why is the column damaged? So trying to track down the reason for it as well as to fix the problem is important. Could be that your detector is contaminated. So therefore you haven't cleaned your detector for a little while. And again, then think about why is it contaminated? Is it because of that extra column bleed going through there because you've got a leak? And it could be electrical noise. So usually we don't suffer much from electrical noise, but occasionally there can be. So always consider that as well. Notes here then, it is chemical noise in our baseline. So that means that it's not separated by our column. Either it's too volatile, it's coming from places like our carrier gas, or it's from the column, or it could be our detector or our mass spectrometer related just on that. And then our final one here is, again, looking at the bottom chromatogram, what we can see is we've got extra peaks. But not only do we have some extra peaks, but that they are broader peaks. And the first peak is in there is actually coming out before our solvent peak. So that's within our void time. So that means then, because it's coming out from in a void time, that it must be carryover from a previous injection normally. So it could be the inlet that is gradually bleeding out from around the outside of the column, getting onto that column, and it could come out a bit early. But also it's a very slow process. Hence it's very, very broad because it's suffering a lot from longitudinal diffusion. Now, if they weren't so broad in their extra places, it could be coming from the syringe or the autosampler. But again, just think about, could it be transferring very slowly from wherever it is onto the column to cause those broad peaks? Could be the injection. But the most likely place for these broad peaks, especially a peak coming out in that void time, is that it's carryover from the previous injections. We stopped the run before everything's come off the column, and then we started the next run, and it then has come off before that solvent peak. So our question number 7 then is, how can the background or ghost peaks coming from the instrument or column be reduced? And what is the most unusual source of ghost peaks you've encountered? I like that question. And I think actually the most unusual one is actually one I've already touched on, but we'll have a look again. So again, then, when we're thinking about this question, background or ghost peaks, where can they be coming from? They must be coming from somewhere which is not where we are normally injected. So the first question is, where could that be, and how is it getting in there, and how can we go and remove it? So again, then, when we're thinking about our autosampler, generally with ghost peaks, we're thinking about our dead volume. So for example, then, so it's probably, ghost peaks probably not going to be coming from our carrier gas. However, if you have exceeded the vapor volume of your liner, then what you can is the solvent will go outside of that liner and it can go back up the carrier gas inline. We'll look at an inlet in a minute. But when it goes back up the carrier gas line, then it comes out in subsequent injections. You might be seeing that peak as a ghost peak for the next 2 weeks with really severe cases just on that. So it could be that carrier gas line it's coming from. But it's most likely going to be coming from a dead volume in our sample flow path. So again, that could be in our alter sampler, could be around the outside of that liner, could be in any column connections, could be a dead volume within our detector as well. Most likely place though for things like ghost peaks, etc., apart from of course our carryover from a previous run, which is what we talked about in the previous question, is coming from our GC inlet. So GC inlet itself is quite complicated. So what we have is our electronic pressure control or pulse pressure control or pneumatic pressure control. Different manufacturers have different names, but it's basically where the carrier gas comes in, and that's going to control the pressure and the flows in our GC inlet, and of course the flow through our column as well. So we have our carrier gas coming in, and then we have our carrier gas going into the inlet. Of course, we have our septum and our septum cap just on there, and we have our septum purge going out. We then have our column flow going out at the bottom, and we have our split flow going out of the side just on there. So we have our split line trap, which is going to trap our volatiles, but as we talked about earlier though, the higher molecular weight compounds might be condensed in that split line trap because of the temperature gradients in our inlet. So we have our inlet body, which is heated. It might be that you have an inlet seal and washer in the base of your inlet, but certainly what you'll have is your inlet liner. So in that inlet liner, that's the site of evaporation and transferring our analyte molecules and our column. So if we exceed the vapor volume of that inlet liner, the sample vapor can go down the septum purge, but then it'll be flushed out or condensed. Down the column, so we can get those peaks going earlier onto our column, we can get split peaks. It can go down the split line, and again, if the split line is open, they'll be lost. If it's not open, they condense in there, and they can come back if we don't open it soon enough. And it can even go back up the carrier gas line, which means that we can get those ghost peaks from that carrier gas line. So of course, those molecules are going to take longer to get onto the column, hence we can have it as ghost peaks. One of the key places for our ghost peaks though is in our septum. So that's the head of our column, our column nut and our ferrule. And of course, the position of that column as well is going to be very important, again, because that will affect dead volume. So if the column is in too far, again, you can get those dead volumes and poor peak shapes and tailing peaks, sometimes split peaks as well, or ghost peaks. And of course, we're going to inject our sample into our GC inlet liner. So we've got lots of places for things to go wrong in our GC inlet, and of course, lots of consumables to go and replace. So one of the things, sources of our ghost peaks is from our septum. So if you imagine your needle goes into your sample, then it goes through your septum, which is, it really pushes its way through there. So you can deposit sample which is on the outside of that needle into our septum. We also get solvent going there as well, and the solvent can eat away at that septum and produce lots of extra peaks as well. So septum purge is important. So what it does is flushes the underside of the septum, and then that can take away any septum bleed and any of that sample, as long as it's turned on and is flowing at the correct flow rate just on there. I have been known though to take 2 weeks just to choose the type of septum to make sure I'm using the right material to reduce the amount of bleed, because some solvents will really eat away at different septum materials. So prevent sample ghost peaks, as I mentioned, from the outside of the needle and high vapor volumes exceeding the capacity of the liner. Helps to remove any septum bleed. So if you're using a mass spectrometer, then septums bleed with certain ions in the mass spectrum, but they can be differentiated. Well, it's not to be confused with column bleed, which have got very, very similar masses in there. How you can differentiate the two is that any bleed from the septum will appear in peaks in our chromatogram, because they are then condensed on the front end of the column when it's cold, whereas our column bleed will only appear generally in our baseline. Of course, if we're using very high initial oven temperatures, then we might have some bleed actually going through our column as well in the baseline. So in terms of the strangest things I've seen with kind of ghost peaks, etc., is things like from the inlet. So either our carrier gas, where it goes and our peaks go up our carrier gas line and then they gradually come out over time, but also as well of peaks basically coming out from our split line. So when we're in splitless mode, they're condensed in there, and especially when you go and have a blocked split line, you haven't got a flow going through there, that those molecules can gradually migrate onto the column, giving you lots of extra peaks, including ones that look like ghost peaks. So of course the inlet purging then is really important, as we mentioned earlier, to remove those residual vapours from outside of the liner, which reduces our peak tailing and septum bleed, and we want to turn that on to make sure it flushes the outside of the liner quite quickly. But yeah, so split line being blocked, carrier gas inlines in the inlet being having extra contamination, those are the two strangest things that I've seen. Now, our final question for this webinar today is, what is the first action to take when no baseline appears on the screen, even though everything else looks normal? So this is really quite hard to imagine this question. So we've got all of our peaks, but we just can't see the baseline. So I'd imagine that the bottoms of those peaks are going to be cut off just on that. So generally, when we are trying to go, if we've got peaks on there, then it's not going to be our carrier gas, because our carrier gas would affect our peak sizes. It would basically, well, our peak shapes, our retention times. And in this question, it's not mentioning any of those problems if everything else is the same. So it's probably not going to be our carrier gas flow path. What about our sample flow path? We're seeing those peaks. So it's probably not the introduction. It's probably not getting onto the column because it hasn't been mentioned that the peak shape quality has reduced. So therefore, then the only thing then, if we don't have any baseline, is that maybe it's our detector that's causing the problem. So especially if you then have things like a set fixed threshold value, you can go and chop off. So in the mass spectrometer, if you don't have if your threshold value is too high, what it does is basically chop off the base of your chromatogram. If you've got something like a flame ionization detector, again, then maybe your auto zero isn't working properly. And actually, you know, the background has reduced so much that it's gone downwards and it's gone below that 0 set point just on there. So it's not reducing it further. So again, you're cutting off the bottom of your chromatogram. So those could be problems then in your software, in your parameters, or in your detector. But those are the first things that I'm going to have a look for. Is there any threshold value or cutoff of what's actually being saved in your chromatogram? So it's going to be basically your detector acquisition parameters. That's the problem with that. But just the final part of this question is also thinking about if you have no peaks. So again, when people say, I don't have any peaks, the first thing is, what do you mean you've got no peaks? So is it that your baseline is still normal and your peaks have disappeared, or is it's affected your baseline as well? So we can see here our baseline is very flat compared to the one at the top. We've got a bit of a negative dip just on there. So when we have no peaks, then examine the chromatogram and go, is it baseline affecting? Is it just the peaks? Where is the problem just on here? So it could be, for example, if the baseline looks quite normal, it just looks like a blank system blank run with no injection, then it could just be that the sample hasn't been reached. So you've got too little in your vial, in your autosampler. So it could be the syringe is blocked or bent, the needle or the plunger. It could be that a gas supply is no gases. So if there's no gas supply of carrier gas through there, you would not see the baseline like normal. Okay, because you won't see that column bleed profile as because it's not then flushing the column bleed through the column and into our detector. So therefore, then it's going to have a different background just on there. Is it that the inlet's cold and it hasn't heated up the sample? So again, then you still got carrier gas going through there. The oven's still heating. You'd still see the baseline, but again, no peaks just on there. Or maybe you might see some of the volatile peaks. Maybe there's a bit of an interruption like we've got at the baseline just in this chromatogram. Could it be that you're getting no flow through the column, not because your carrier gases are turned off, but because you have a blocked column? Maybe the column is broken. One of the hardest things to troubleshoot is when the column is broken partway through. That's really hard to identify, or that you've got a crack in it just on there. It could be that the detector's not off. It is off. You're just not running the detector, so you're not going to produce a chromatogram. So again, then you're not going to see the column bleed in that example. So again, so you can go through your system going, yes, it could be this, but then think, right, if it was this, what would I see in my chromatogram? Would I see a baseline or wouldn't I see a baseline? Would I see a solvent peak or wouldn't? So if you've got a nice solvent peak, but no peaks, maybe you're accidentally analysing a solvent blank instead of the sample you're expecting. Maybe you had them in the wrong place in your sampler tray. So that brings me to the end of some of the questions that you've sent in. So thank you very much for sending those questions in. They are really, really interesting and all really good questions. And hopefully I've managed to answer some of those questions today and also give you lots of other information about how to go about your troubleshooting. So whatever problem, you know, if you have your instruments working really well right now, unfortunately, you will have a problem at some point. So always be as prepared as possible so that when you do have a problem, you can troubleshoot it and fix that problem very, very quickly. Thank you very much for listening.
Thank you, Diane, for that excellent presentation, and everyone who helped shape this webinar by posing a question. Thank you also to our scientific partners in this webinar, ACD Labs. Finally, I would just like to remind everyone that a recording of this webinar will be made available soon, and you will all be sent a link to this. And with that, I'd like to thank you all for logging in and watching. Thank you, and goodbye.